Hey everyone, James McBride here. Let's take a look at the basics of wireless networking, or what we call Wi-Fi. Now, really, to understand this concept, you have to understand what Wi-Fi is, and that is a set of radio waves within a certain specification. So in this little tiny picture over here, it's big enough for my illustration. This is visible light, and there are radio waves below that visible light and above it. And most people are aware of that topic. So you need to understand that this type of radiation, it's an electromagnetic radiation, means it's electricity and magnetic. So it's electromagnetic radiation, similar to light waves, but with longer wavelengths. They are used for various applications, including wireless communications, which we're going to talk about, broadcasting, radar, and satellite communications. So we use radio waves a lot. And when we talk about Wi-Fi, that's a certain set of radio waves. Let's move on. There are two important terms to understand, which is propagation and frequency. So propagation is the transmission of motion, sound, or light. Therefore, the propagation of radio waves is the way various radio frequencies move through the air or the surface of something. So propagation is how those radio waves move through the air or through something. Frequency then refers to the number of oscillations or cycles of the radio waves that occur in 1 second. It is measured in hertz. So if we go back to our little tiny picture here, you see these big waves, and then you see these tiny waves. Oscillation is referring to the process of from the tip of this wave to the bottom, to the tip, to the bottom, and on and on. So how soon do we see those? And then we rate those according to a hertz, megahertz, gigahertz, or hertz. Hertz is really low. So if you were to take a sample of the actual wave, it would be from here to the next. So you have that full wave, right? From top to bottom to top. Now, the truth is that that is a very two-dimensional look at a radio wave, but we don't need to get into it any more than understanding that this frequency means that the radio wave, when we get into megahertz and then gigahertz, that frequency is more compact. It's pressed together, as we'll see. So things you need to know about propagation, and basically that means, right, how that radio wave is moving through the air or something. Distance. The strength of the radio signal decreases as the distance from the transmitter increases. It's a very scientific way of saying, hey, if you got an antenna and it's pushing a signal out of that antenna, the further that gets away from the antenna, the more it decreases. So you have to have a certain amount of energy that's pushing that radio wave in order for it to go as far as you want it to go. And that often depends on the frequency. So if that's true, then any obstacles, buildings, trees, water, metal, whatever, can affect these radio waves and can even reflect the radio waves back. And that affects the path that they're traveling on. This will all come into understanding as you see this is how Wi-Fi is implemented. And then, of course, extending that into these are the problems with trying to keep it secure. Atmospheric conditions can affect things. Weather, stuff that happens in the ionosphere can influence how these waves travel. Now, for Wi-Fi, the ionosphere is not going to be a problem, but if there's rain falling, that's something that's going to affect how far that radio wave can go. Frequencies and wavelengths, different frequencies and wavelengths behave differently. For example, lower frequencies can travel longer distances. They require less power, and they penetrate obstacles better than higher frequencies, which we reiterate in a moment. So that's important to note. If you are choosing something that's got this really, really low frequency, meaning that, it's a big wave, that wave can travel through objects better. That way, in our understanding, and this is really getting more difficult to explain because a lot of people don't even use FM radio or AM radio or anything. The AM radio wave is much bigger than FM. FM is really big. So you can sit in a building and pick up an AM radio station But some buildings you can't pick up FM very well. And then those radio waves, because their frequencies or wavelengths are so much bigger, they get into a building much better than, say, a cell phone, which has a much smaller radio frequency. So these wavelengths really affect things. The United States, I watched a show on this years ago, the way they send a signal to a nuclear submarine is they trail out an antenna that's a mile long, because the radio frequency that they're using is a mile long. You have to have that distance to capture the whole frequency. And so you can't send much on that, right? But all they're sending is, a few digits, basically a letter number combination. And then they look in the book or on their computer and it says what that letter number combination means. Nuclear subs are used for basically deterrence. If you launch a nuclear strike on the United States, you don't know where their submarines are. And all it takes is some station within the United States that can do this and send out a code that says launch, this is where you're launching to, and away you go. And so they have a whole set of codes in these books and these computers that just tell them F476543B means this. So they don't have to send a whole lot, but the radio frequency they're sending that on, that wavelength is so long that it'll go through the earth. Wherever that sub is, they'll be able to get it. And I use that just as an example, right? 2.4 gigahertz that you use inside, that's what our Wi-Fi is mainly. That can't go that far. It can't go nearly that distance. It falls apart. The other thing that affects this propagation then is the antenna design, the orientation of that antenna. How you design to push the signal is what this is referring to. There's antennas that are dishes, right? And they focus the beam to a certain place. And then there's antennas that are just poles, and it just shoots the signal out around it. That antenna design affects how far it can go, or the propagation of it. Modes of propagation, and threw this in just so people would know, we're dealing with line of sight, but yeah, you can actually shoot the radio waves through the earth and use it as a way of communication actually through the earth. And I don't necessarily mean right through, like I mentioned with the other, but say you're going over a short distance, this building to this, you could push it through the earth. And then of course, skywave propagation, that's much more seen in ham radio operations, AM radio operations. The waves are reflected back to the earth by the ionosphere, so it can't get out, and then it bounces back down. And that allows for really, really long distance communication. That's what ham radio operators have their fun doing. They got a massive tower and they're talking to people all around the world because of this reflection off the ionosphere. And then, of course, what we're dealing with is line of sight propagation. The radio waves travel directly from the transmitter to the receiver without significant reflection or refraction. This mode is crucial for applications like satellite communications and radar, and for Wi-Fi. Line of sight is important. All right, these are our common radio frequencies that we use in wireless communications for computer systems and phones, anything along those lines. 2.4 is by far the biggest, and I don't mean it's not just the biggest frequency, because it is the biggest frequency. It's the most used because its ability to penetrate obstacles like walls. It can go through walls depending on what those walls are made up of. The 2.4 frequency is about an inch long, and so something that's over an inch thick is going to stop it. It'll reflect off of it or absorb the signal. For instance, if you have a tree in the way of something that you're sending, part of the signal is going to bounce off that tree. Part of it's just going to be absorbed by the tree. So radio frequencies are really, really complex. It's not that straightforward as running a cable. But 2.4 will go further. It doesn't take as much power to push it as far, and it can wrap around objects, bend around objects, and go through anything that's, less than an inch thick pretty well. And of course, density is an important factor on that too. So it doesn't take an inch of steel to really mess with this. It can be actually quite thin and really mess with the frequency. Then we use 5 gigahertz. So 2.4 and 5 are really, really heavily used. This band offers higher data transfer speeds and less interference due to more available channels. So what they mean here is that in 2.4, we're really using that everywhere. And basically you're dealing with about 11 channels there. It really depends on what nation you're in. They all do it. They don't all do it differently, but there are several nations that do this different than what we do. And so you choose channel 3, and then because 2.4 is used so heavily, your neighbor that's not too far away from you also uses channel 3, and that's interference that you end up with. So 5, there's not as much people on that. That's what they're talking about here. However, 5 has a shorter wavelength. Therefore, it has less range and is less effective at penetrating obstacles. And so 5 gigahertz, you're going to want to be closer in order for that to work. Now, something I forgot to put in here, and I'm sorry for that, is the more you see the oscillation, the wavelength itself. So if the wavelength is condensed, you have the ability to encode data along that wavelength more. And that's because you're seeing that top to bottom more frequently. So you can encode data on there, where in the longer wavelength, you can encode much less. Like I said, something that has a wavelength that starts here and then a mile later comes back to the same point. Wow, that's a long wavelength, not much data you can put on that. However, 5 gigahertz going up and down, up and down, up and down, you can encode more. That's why within our Wi-Fi, if you can use 5 gigahertz, then you're getting faster transmission speeds than 2.4. And now 6 has been added to that. So that would be known as Wi-Fi 6E. Wi-Fi 6 is currently really getting predominant, and that basically ties these two together. More information on that in another video. And then this one is even higher, right? That's oscillating even higher. It's a much shorter wavelength, and so you can encode even more. However, it has the shortest range among these three. It's important to realize that you're using these different frequencies, and in Wi-Fi, this is what it is now. 2.4, 5 gigahertz, and now we're adding 6. That's Wi-Fi. It's not cell, that's Wi-Fi. So attenuation is how bad does this fall apart as it goes through the air? So it refers to the reduction of the strength, force, and intensity of something. In our context, it means a decrease in the signal strength as it travels through the medium, such as the air, walls, and other obstacles. But mostly right through the air. This is what we're trying to do most of the time. The lower the frequency, the better the radio wave moves through the objects, as I explained. 2.4 has a longer wavelength than 5 gigahertz, which allows it to diffract or bend around obstacles more effectively and penetrate through walls and other barriers with less attenuation. Okay, let's look at actual implementation of Wi-Fi. So when you see, again, that term Wi-Fi, it means 2.4, 6 gigahertz, 5 gigahertz. It's the main ones that we use for our wireless networking. Wi-Fi just refers to wireless fidelity, and you see this happen a lot of times in computers where some kind of marketing term is thrown out there so that the normal people, the average person, can pinpoint what that is. Instead of learning 2.4, 5 gigahertz, and 6 gigahertz, and that's what our wireless networks are, you just say Wi-Fi. That's the term that we use, and this is the stuff right here that you need to pay close attention to when you're actually implementing a wireless network. Well, let me give you an example. Let's just take one from home. Basically, you or your mom or dad or your aunt or uncle or somebody said, hey, we need wireless network. And what happened was you have network coming into your house, and that's cable or it's fiber optic, or maybe it's actually a big wireless antenna up on your house. It can be that too, or it could be a satellite dish that's receiving that. And you want Wi-Fi in your house. You want wireless networking. So usually wherever that's coming out at is where they stick that little wireless box. And really, when you go to work someday, that's not what you want to do. You don't want to just say, well, the line's coming in here, so we'll just put the antenna here. The following is why you don't want to just do that. First, you have to consider building materials. Are there walls around you that are just concrete and you're expecting that wireless box sitting on the other side of this massive concrete wall to actually penetrate that and get into the other room, which it's going to have a tough time doing? I had a person that they were in an older house and it was an Adobe house. And they're like, yeah, the Wi-Fi, my house is so small and the Wi-Fi is just in the other room and I just can't get it. It's such a weak signal. I was like, well, what's your house like? And then they told me, and I was like, oh, that's an old house. So those are all your internal walls are Adobe. So not just the outside, but your internal walls are all Adobe construction. Yeah, it's not going through that. What? Yeah, Wi-Fi is not going to go through that. It's going to be absorbed into that wall. You have to think about what it's been constructed with. Concrete, metal, they significantly weaken the signal or attenuate the signal. The distance, how far does it need to go? How big is that house? I deal with a lot of people that would be like, they'd say, oh, I got a really terrible connection in this part of my house. I was like, where's your wireless router? And they go, oh, well, it's over here. Okay, well, where is this location you're talking about? Oh, it's in the basement across the house. So how big's your house? People don't understand this attenuation. They don't understand, well, yeah, now you're trying to send a signal down into the basement and it's having a hard time getting there. And the distance of one end of the house to the other is way too far. So where do you expect the signal to go? Obstacles like walls, furniture, and everything can reflect, can block, can cause weaknesses. It can also do a multi-path effect where the signal takes multiple paths to reach the receiver. It's kind of split and trying to get there. That means it may not even show up at the same time. And then, of course, there's interference. Other electronic devices operate the same frequencies, such as microwaves, cordless phones, can cause interference, reducing signal quality. And usually in class, somebody will go, oh, that's why, I can't, when I'm sitting there waiting for my hot pocket to get done, that my cell phone is not picking up the Wi-Fi that great. It just kind of like starts timing out. I'm like, yeah, get another microwave because it should be blocking more of those radio waves than what's coming out of that thing. It shouldn't be causing that kind of problem. This interference as well can be from a neighbor on the same channels. Penetration, 2.4 signals, as mentioned, can penetrate walls and obstacles better than higher frequency signals like 5 gigahertz, but they still experience significant attenuation through very dense materials. Reflection and refraction. Reflection means it's going to bounce off. Refraction means it's going to separate. Radio waves can bounce off surfaces or bend when passing through different materials, refraction, leading to complex propagation paths, as mentioned in the previous page. And then that multipath effect coming from this, an indoor environment, signals often reflect off of multiple surfaces, creating multiple paths to the receiver. This can cause constructive or destructive interference, affecting the signal strength quality, meaning that multiple paths might help you or they're going to hinder you. And that really just depends on the timing, right? If you've got multiple paths, but that radio wave is then hitting at the same time, you're good. You're good. That's going to be okay. But quite often, those multiple paths have some kind of obstruction. So this one's going to reach first, and then this one's going to come in second, and then you've got an issue. So all these things affect wireless communication, and that's really important to remember because you have to ensure proper coverage. So from a networking standpoint, you're putting in this Wi-Fi and you need to know where you're going to put it and where it's most effective to put it in order to provide the networking that you need. Also, you need in security, like, am I just propagating all this out my window then more than in my house? And that happens a lot in people's home network. They have that Wi-Fi box and it's sitting right next to the wall. And then it's got to hit the rest of the house. And so a lot of it's going outside. Anyway, it's important to place the access point in strategic locations so that you can minimize the obstacles and interference. And using multiple access points can help cover larger areas. Within an organization, that's what you're doing. You're going to have multiple access points. Signal strength, you're going to monitor and optimize that strength coming from these multiple access points. And you'll use tools like Wi-Fi analyzers to help you understand what kind of radio signaling is happening. Now, lastly, just quickly, the problems that this causes with security, which I've already been kind of hitting on. The propagation means that Wi-Fi signal is broadcast through the air and can be intercepted by anyone within range, even outside the building. This makes it easier for attackers to access the network with no need to have physical access. So they can sit outside your building and try to hack it. Interference. Wi-Fi networks are more susceptible to interference than wired networks, with all those other electronic devices that might be transmitting on that frequency, which can be exploited to disrupt your network or capture data. In other words, somebody next door is using channel 3, as I said, and you are, and that's interference. Well, there's also the malicious intent of that, looking at somebody's network and going, they're using channel 5, so I will just broadcast a bunch of junk on channel 5, and that disrupts the entire signal and gets rid of it. And then, of course, eavesdropping. Attackers can use tools to analyze the Wi-Fi traffic, potentially intercepting sensitive information. And that comes back to the propagation, right? It's going all over the place, so they can eavesdrop better on that. Thanks for watching. I appreciate the time that you've taken, and we will talk with you later.